Hello everyone. Today it's finally here. The 2025 May past papers are out. And today I'll be solving the problems that are kind of new to the syllabus. And so we'll start with number 12 right away. So this question is about paper chromatography. And so this question is telling us that naphthalene and naphthol was placed in the baseline and polar silica was used at the stationary phase and nonpolar hexane was in the mobile phase. And so we want to find naphthalene if that's Y or X. And so we can see naphthalene is a non-polar molecule because it's symmetrical. And naphthol has an OH group, meaning it can form hydrogen bonds, meaning that it's polar. And so this question is saying that the non-polar hexane is our mobile phase, meaning that naphthalene and the mobile phase is going to dissolve with each other because like dissolves like. And so since the mobile phase moves up more, naphthalene will be X, naphthol will be Y. And so we can cross out A and B. And between 0.8 and 0.3 for the RF value, the RF value denominator is the distance that the solvent traveled, which is from the baseline to the solvent front. And so since this is 1, 2, 3, 4, 5, and 6, the solvent traveled 5 and our solute traveled by 4. And so 4 over 5 gives you an answer of 0.8, giving an answer of C. Well, heterolytic bond fission was also new. So what does heterolytic bond fission mean? Hetero means different and lytic means break. And so you got to break the bond and it forms two different species. And so that would result in C. So the two electrons move to one Br, which forms Br plus and Br minus on the other bromine. And so for time zone 2, we can see some separation methods that were present here. So a test tube contains a mixture of liquid hydrocarbons. So hydrocarbons are all non-polar molecules because CH bonds are non-polar, right? And so what is the type of mixture and the best method of separation? So first, liquid hydrocarbons, since they're all non-polar, they're going to mix in equal amounts, an equal distribution in the solution, meaning they're going to be homogeneous. And so if you want to separate two mixtures, then you got to use distillation, which will give you an answer of A. So distillation was you have like your solution here and you have a little way out for your gases. And so if you have solution number 1 and solution number 2 and the boiling point of 1 is higher than the boiling point of 2, then if you heat the solution, the number 2 is going to evaporate first. But gases is going to fly away, right? So gases must be cooled down using cold water, which would result in condensation. So your gases will turn into liquids and then you can filter out number 2 again. So this process was called distillation, yeah? And so there was another paper chromatography question. So if we do this really quickly, X, we're finding the RF value of X. So the solvent traveled this much, which is a total of 28 millimeters. And our solute traveled by 21. And so the RF value can be calculated as 21 over 28, which would result in a value of 0.75. This question was kind of new. I've never seen it before in the past like 10 years. So which equation correctly describes a chemical reaction? And so if you look at A, HCl and Na2CO3, so that's an acid plus carbonate, should give you a salt, CO2, and water, which is perfect. And the equation is all balanced as well. So the answer here would be A. B is our trap because Cu plus 2HCl, which is a metal plus acid, should actually give you a salt and H2 gas, which is what the equation states. But you guys need to remember that Cu is a non-reactive metal. And so Cu cannot react with HCl. And so this question B, this equation B is not possible. For C, that's wrong, right? Because base and acid should give you salt and water. And so that's why C cannot be possible. And D is the same as A. Acid plus carbonate should give you water and CO2 as well. So D cannot be the answer here. Number 35 is kind of new because this also asks you to find the pH of a buffer solution. And so it tells you that methanoic acid is present at 0.5 moles per dm cube, sodium methanoate is 0.25 moles per dm cube, and they give you the pKa of methanoic acid as 3.75. So if you don't know how to solve a weak acid base question, then first write the equation for methanoic acid's dissociation. So methanoic acid is HCOH, and this would partially dissociate to H plus and HCOO minus. And so if you write the Ka for this methanoic acid, this is 10 to the minus 3.75. And this equation would be HCOH on the denominator, H plus on the numerator, and HCOO minus on the numerator as well. And if you take a look at the question, they give you all the info we need because we want the pH, which is this, H plus. This is what we want. But they give you that methanoic acid is 0.5, so that's 0.5. And sodium methanoate is 0.25. And so we can calculate for H plus. So if you calculate H plus concentration gave you a value of 3.56 times 10 to the negative 4. And so if you want to find the pH is just basically minus log that thing. So 3.56 times 10 to the negative 4, which would give you an answer of 3.45, giving B. And so some schools also teach you this equation called the Henderson-Hasselbalch equation, which is pH is equal to pKa plus log HA on the denominator and A minus on the numerator. And so they gave you everything. pKa is 3.75, so you put that there. A minus is the salt or the conjugate base, which is 0.25. And HA is our acid, which would be 0.5. And so if you substitute it, you would get exactly the same answer as 3.45. So now we'll start with paper 1B. So 1B was new to the syllabus, and I think these questions are kind of tricky. So what would you need to write to get all 4 marks? So first, a student was given a mixture to separate and collect the individual components of, you have sand, SiO2, you have salt, NaCl, and you have iron. So I want you to pause and think about what you would do to separate all of these 3 components. So first, you may have thought of, sand and water. Then you can separate them using dissolution, because salt dissolves in water while sand does not. But the problem is Fe. What would you do to separate iron? So remember that iron is a metal. So you would first need to use a magnet to remove iron. And then you would add water to dissolve NaCl. And so your solution is going to have salt water and sand that's not dissolved. And so what you would do is you would filter solution to obtain sand. But there's 2 problems now. So first, sand is still wet. Yeah, but if you want to get rid of the water, you would need to heat sand to dry. And the second problem is that the salt is dissolved in the water. And so you would want to evaporate water from NaCl. And that's how you would separate the 3 components. Good, so the following data was collected where the mixture before separation, so the whole thing was 5.62, iron, sand, and salt have their masses respectively. So how would you find the percent composition? So your total mass is 5.62, and iron would be 2.17 times 100, yeah? So this would be for iron, giving you a value of 38.6%. In the case of sand, sand is 1.98 divided by the total mass times 100, which would be the sand, which would give you a value of 35.2%. So C, the percentages in B add up more than 100. So suggest a reason that would explain these results and how to reduce or eliminate it. So usually percentage yield is less than 100. It's very hard to get more than 100. But in this case, it is more than 100. And the reason why you get more than 100 is because water remained in sample. So almost all the questions where I saw percentage yield was above 100 was because of the water. So when you take out stuff from water, it's always gonna be wet And even if you dry it, there's going to be some water that did not evaporate yet. And so how would you reduce or eliminate it? This is a very commonly used lab technique. You heat until mass becomes constant. Super important. This comes out so much. What's another example? Like Mg and O2 reacts to form MgO. And so first, your Mg is in a crucible, you heat it up to make MgO. But how do you know your reaction's completed? You heat until the mass becomes constant. What's another example? You have BaCl2 with water. And so you heat it up to get rid of the water. And how would you know that all your water evaporated? Heat until the mass becomes constant. So this comes up very often, so I want you guys to remember this one. And so D, the results did not support the original hypothesis, suggest why the hypothesis was incorrect. Hypothesis, what was it? The iron would have the lowest percentage by mass because it appeared to be present in the smallest quantity. So if this was your sample, initially iron was just like this much, while sand and salt was present in excess. So that's why the person initially thought that iron would have a small mass, but it did not turn out that way. It's actually the largest. So many people wrote here that Fe has a high molar mass, is what people wrote. But that's not the case. You cannot write high molar mass because molar mass just tells us how heavy a substance is, but you did not mention the small volume part. So this has a small volume, but why is it so darn heavy? In this case, you need to say that the density of Fe is high. Because what was density? Density is mass divided by volume. So now you take into consideration the volume. So if density is high, it means that even if you have a small volume, the mass of iron will be very, very high. So you need to write density here. And then for E, in a different experiment, the students needed to separate a mixture of methanol and butan-1-ol. So state the best method to separate this mixture and the physical property used for the separation. And so methanol, butan-1-ol, they are both alcohols, meaning they will be miscible, meaning that they can mix together, right? And so this would require distillation. And the reason why we can use distillation is because they have different boiling points. And to review, who has a higher boiling point? Methanol has 1 carbon, whereas butan-1-ol has 4 carbons with an OH. And so you cannot write about A has a stronger hydrogen bond. No. You need to talk about London dispersion forces being stronger for butan-1-ol. Why? Because they have a longer carbon backbone, so they have a greater surface area of contact. That's why they have stronger LDFs, leading to a higher boiling point. Okay, now let's move on to time zone number 2. So the concentration of calcium ions in aqueous solution can be determined by titration with ethylene diamine tetraacetic acid, so EDTA, or by atomic absorption spectrophotometry. So EDTA solution must be standardized before use by titrating it with a standard solution of calcium chloride. And so an accurately weighed mass of powdered calcium carbonate was dissolved in concentrated HCl and heated to remove all the carbon dioxide. After cooling, the calcium chloride solution was made up to exactly 250 cm3. And so state the most appropriate glassware to make 250. You need to use a volumetric flask. Never, ever, ever write measuring cylinder. Measuring cylinder is like the worst thing you could use. So volumetric flask, yes. But you might be like, Sam, Sam is a teacher in Korean, by the way. So teacher, can't we use like a burette or a pipette? The problem with that is this volume is too large. So for large volumes, you use volumetric flask. For smaller volumes like 25 cm3 or 10 cm3, you use a pipette or a burette. So number 2, describe the steps involved in preparing the standard solution by dilution of the initial calcium chloride solution. And so you're using a concentrated stock solution to make a dilute solution. So what would you first need? You would first use stoich to determine the volume of concentrated solution required. And how would you do this? You would use the equation C1V1 is C2V2, right? And so that amount's going to be very small. So you would use a volumetric pipette to measure concentrated solution, and you would pour it in the volumetric flask. So you take a small sample, you put it in the volumetric flask, like a 250 volumetric flask, and then you fill it up to the line, is what you need to do. Okay, and then B, calcium chloride is not used to make standard solutions because it readily absorbs water, meaning that it's gonna form something like this. So a hydrated solution, a compound. And so suggest how a solid calcium chloride could be treated in the laboratory to remove all the absorbed water. So we just saw this, yeah? You wanna heat it up until all the water evaporates. So you wanna heat up the sample until mass becomes constant. So please remember this, yeah? And then C, a sample of tap water was titrated against EDTA using Erychrome black tea as an indicator. And the following titration data were observed or obtained. And it's asking, suggest 2 reasons why volume added in trial 1 is much larger than the other values. So if you look at trial 1, that's 26.15, while the rest is about 24.3-ish, yeah? And so you might have done titrations in school. And in titration experiments, you need to be very, very precise. You put 1 volume, mix, and see the color change. If there's none, put another volume. So another drop, another drop, another drop. But if you start that from 0, this would take you like 8 years to do. And so you first do a rough trial. So you put it in really fast, and if you see a color change, you write it down as 26. So on your next trial, you would put it really fast until like about 20, and then you will start your experiment very, very precisely. And so the 2 reasons is, first, titration is done quickly, is what you can write. Or there could have been an experimental error. Like for example, your burette leaked. So if your burette leaked, you would use a larger volume. So burette leaked is another possibility you could write. And another thing you could write is that you would want to clean your solutions with EDTA prior, because if there's like water inside your burette, then it's gonna lead to a more dilute solution. So flask was not cleaned with EDTA would be another problem. So there are a lot of experimental errors that could be present in this experiment. And so if there are experimental errors, you'll have values that differ significantly from others. And what do we call that? We call them either anomalies or outliers, is what we could call them. And suggest a reason why trial 1 should not be used when finding the mean volume of EDTA used. And so, since that volume is too high, it's gonna lead to concentrations that are too high. So calculated concentrations are too high, is what you could write. Or you can say that the values are not concordant. And what does that concordant thing mean? Concordant means, like if you look at these 3 values from 2 to 4, the difference is about 0.1 cm cube difference. In a titration experiment, each trials should have a difference of about 0.1. And if you don't have a difference of 0.1, you should do more trials so you can get about like 2 to 3 concordant values for you to use in your IA. Okay, now the next one is B. So the average results from A were graphed. So this is another question. It's not the question above. So this question was about spinach, and they're boiling spinach, and we're trying to find the amount of Fe2 plus in the solution. So state the relationship shown in the graph between the amount of Fe2 plus released from the spinach and the boiling time. So people, when they read this, If there's like a relationship question, they're like pressured to write, oh, it's like positively correlated, or it's like an inverse correlation. But if you look at this, there's just like no correlation. So you can just write no relationship. But if you really, really want to write something about relationship, then you can see that it kind of decreases till 15 and then increases back at 20. So you can write that there's a negative correlation to 15 minutes, then positive correlation. But I don't really like the second one. I would prefer the first one much better. Okay, and then comment on the range and quality of measurements used in the investigation. So what are they talking about when they're talking about the range and quantity? So the range is talking about the boiling time. So from 0 to 20. Do you think that's adequate? But to be honest, I think it is adequate. Because when you're boiling spinach, you would boil them to like a max of 20 minutes, right? Like you wouldn't boil them even longer. So I would say that the boiling times are realistic. So yeah, I'm Korean, right? So if I eat spinach at home, usually like 10 minutes, 20 minutes would be sufficient. But, you know, some other countries may boil spinach for a longer time. And if that's the case, you can say that that's a narrow range. Like, oh, our country boils spinach for like an hour. And so you would want to extend your experiment for about 60 minutes. And quantity. So the quantity talks about is 5, 10, 15, 20 minutes enough? So is the increment of 5 minutes enough? But I think it's not enough because you do not know how much they decrease. Like, is it like a linear decrease like this? Would it become like this? Would it become more like a parabola? That we don't know. So I would say there are insufficient intervals. But I think the biggest error in this experiment is that there's no measurement of t equals 0. So measurement of t equals 0 needed or required. And why is that so important? Because you don't know where it starts. So if it were here, then basically it's showing us that, oh, boiling time does not have a significant impact on the amount of iron. But if it were like here, there's a huge decrease. Now this tells us that, well, the boiling time is not that important, but as soon as you start to boil the spinach, that decreases the Fe2 plus concentration by a large amount. And so in our conclusion, we could talk about how when you're eating spinach, you should eat them raw and not boil them, right? So that's why the initial concentrations are very crucial for this experiment. And for time zone 3, this was kind of weird. I've never ever seen a question like this before. So you want to draw a table that can be used for recording the results of the titration experiment described in part E. So what you're trying to do is, you're trying to just put in NaOH and measure the volume of NaOH required to reach the endpoint. And so people are like, what do I need to write? But for a titration experiment, you remember that you have an initial and a final volume. And you calculate the difference to find the amount of NaOH used, right? And so in your table, you need your initial volume and you would need your final volume. And if you're doing experiments, how many trials do you need on average? In chem, trial 2, trial 3. So you would usually have about 3 trials. If you have a lot of time, then 5 trials would be even better. And so you would make your table like this, and you're good to go. But actually, you're not good to go, because if you read carefully, it says include units. So for the volume, you would want to write cm cubed, and the final volume, you would also want to write cm cubed. Yeah, so this was kind of new. So you could see that from paper 1B questions, there's a lot of experimental stuff going on, and it's almost like an IA. So this, very IA-like. The methods, that's also very IA-like. And the errors, those are also IA-like because you write them in the limitation and evaluation section. And so number 2, in a separate experiment, the rate of reaction was studied using colorimetry. So during the reaction, the mixture changed from orange to green. Oh, orange to green, so that would be something like Cr2O7 minus to Cr3 plus. So dichromate, yeah? So before the investigation should be carried out, it was necessary to construct something called a calibration curve. So before we move on to calibration curve, we could do question A. So describe how a standard aqueous solution can be prepared. So standard aqueous solution is basically you have a solid, you put it in water, and you mix it. But you would want to write that better, right? So first, you would need a known mass of a solid. And what do you do to the solid? You would dissolve it in distilled water. So distilled water, unionized water, pure water, really important. Why not just tap water? Because tap water has a lot of impurities inside which will interfere with the colorimeter. So the absorbance value that the colorimeter gives you is going to be skewed. So you got to make sure you're using distilled water in all these experiments. And so what would you use? You would use something called a volumetric flask. And you would fill up to the line. So IB really loves this. They really love the use of a volumetric flask. So please remember to write that, yeah? And so B, describe how this solution can be used to construct a calibration curve. But schools don't really teach you what a calibration curve is, right? So that's what I'm here for. Let me tell you what a calibration curve is. So you may know that CuSO4 solution has a color that is blue. This you need to know. So IB kind of infers or thinks or assumes that you already know that CuSO4 is blue. And you should know this because it is my favorite color. So search it up on Google. So yeah, I have two solutions. First one is just kind of light blue. And the one on the right is very, very dark blue. And so we would know that the one on the right is a bit more concentrated. But why is CuSO4 blue? Is it because it absorbs blue color? No. So if I draw the color wheel, let me just draw it more evenly. Color wheel would be red, orange, yellow, green, blue, violet. And so if you remember, CuSO4 is blue because it absorbs the complementary color of blue, meaning that it absorbed orange. And if you compare the two solutions, the one on the left would absorb just a bit of orange, while the solution on the right would absorb a much, much higher quantity of orange light. And so if you use a colorimeter will give you the absorbance. Let's say this is 0.35 and this is like 0.85. But how would you change this into concentration? So how would you find this in moles per dmq? That's why we need a calibration curve. So in order to obtain a calibration curve, you will first need to prepare some solutions. So let's say I have 6 solutions and their concentrations are all in moles per dmq. So CuSO4, you're going to prepare them as 0, 0.1, 0.2, 3, 4, and 5. And so the first one is going to be colorless. The second one's going to be slightly blue. The second one's going to be a bit more blue. Third one, a bit more. Fourth one, a bit more. Ooh, this doesn't really work well. A bit more blue. And the fifth one would be very blue. Yes. Oh no, see, this is what always happens. Let's just say this is very blue, yeah? And so what you would do now is you would measure the absorbance of each solution. And it's really cool because if you get the correct data or if you do your experiments well, they should all be directly proportional. 0.4, 6, 8, and 1 is what you're going to get. And so if you go back and you try to draw the curve, you put concentration of CuSO4 on your x-axis and you get absorbance on your y-axis. And so if you draw your straight line, that is your calibration curve. So what you would do now is, remember, our absorbance were 0.35 and 0.85. So you put 0.35 on the y-axis and you move in the curve. And so 0.2, 0.4, it should be somewhere in between, right? So this concentration would be 0.125 moles per dm cubed. In the case of the 0.85, you'd move here and you move down. And 0.85 would be between these two values, right? So between 0.4 and 5, giving you a concentration of 0.425 moles per dm cubed. And this is how you use a calibration curve. And so if you go back to our question now, this is easy peasy. So describe how the solution can be used to construct a calibration curve. So you would first make solutions with different concentrations. And then you would measure absorbance for each solution. And then what would you do? You would plot absorbance versus concentration of solute. And there you go. This is what you need to write to get full marks on the calibration curve. Okay, then let's move on to the paper 2. So you have a mixture of CO2 and H2 in a molten carbonate fuel cell, which is similar to a hydrogen fuel cell. And so deduce the half equations for the reactions occurring at each electrode. So if you look at the anode, oh, you might be like, okay, this is just redox stoichiometric balancing stuff. So oxygen, if you want to match oxygen, you added water. And then if you want to match the hydrogens, you added H+, right? But that's weird because the charge is all balanced out. But this is the anode. And in anode, oxidation must occur. So this would not be it, right? So what do you need to use to match the hydrogens? If you look at the anode, H2 goes in the anode, meaning that H2 will be a reactant. And so in the anode, instead of writing H+, you would write H2 instead. So you always need to look at the reactants in a fuel cell because those will be part of your equation. And just to match the charge, you would just put 2 electrons on the right. In the case of the cathode, CO2 becomes CO3 but O2 is added in. So in order to match the oxygens, you don't add water in this case, you would add O2 inside. And to match the charge, you would just put 2 electrons and you'll be good to go. So always take a look at what reactants you have, okay? So D suggests why molten carbonate fuel cell is considered to be environmentally friendly. So if IB gives you anything about environmentally friendly stuff, then you always need to talk about the carbon dioxide. And there's one here in the products, one in the reactants. So net production of CO2 is 0, is what you just need to say here. Or you can write like no contribution to global warming. That would also be A-okay. And C, Born-Haber cycle. So this syllabus is different from the last syllabus because you don't need to draw the whole Born-Haber cycle yourself. So they're going to give you this and you just need to fill in the blanks. So first, let's fill in this. Enthalpy of formation of CaCl2. So enthalpy of formation was you're trying to form CaCl2 from its elements in their standard state. Elements, Ca solid, Cl2 gas. So those are your species present. And then what's this process called? So Ca becomes Ca2+. So you're removing an electron from an atom in its gaseous state, meaning that's ionization energy, but this would be the sum of first and second ionization energies of calcium. So remember, always write the sum of first and second, yeah? And what would this be? So this is the products of the lattice enthalpy. So lattice enthalpy was the enthalpy change when 1 mole of a solid ionic compound is converted to a to its gaseous ions. So you are trying to make Ca2 plus gas and 2Cl minus gas, and that would be your species present. Okay, then B. So this question is not new, but I gave you this because when you're changing temperature from Celsius to Kelvin, you would add what? Would you add 273 or would you add 273.15? So the data booklet says 273.15, but the mark scheme says this. So if I show you how this question was solved, you're trying to find moles, which is PV and RT, because they're all gases. And if you move the equation around, and it's PV divided by RT. So pressure is 10 to the 5 pascals. Volume is 55.7 centimeter cubed. But Pascal should always go with meter cubed. So 55.7 times 10 to the minus 6 meters cubed divided by R, which is 8.31 joules per mole Kelvin. And the temperature is 100 degrees plus 273 is what the Mark scheme said. So they did not add 273.15. And this would end up in a value of 0.00180 moles. So the question, so IB did not really say anything about this yet. And so I will keep you updated on information on what we need to do with temperature. But I think that if you added 273 or 273.15, the IB will both mark it correct. So time zone 2. So time zone 2, discuss the products at the electrodes when aqueous thallium sulfate was electrolyzed. And the electrodes were both inert, by the way. And so if I draw you a electrolytic cell, really quickly, it would look something like this. So the left side is the positive, right side is the negative electrode. And what is inside your solution? So you have TL plus, you have SO42 minus, and water. And so TL plus water goes to the right, SO42 minus and water goes to the left. And so who reacts on the anode? So the left side. We said polyatomic ions such as SO42 minus, CO32 minus, NO3 minus, PO43 minus, they never react on the anode. And so it's only water. And if you write the oxidation equation for water, water becomes 1/2 O2 plus 2H plus 2E. So it only asks for the products, so you just need to write O2. And so the reason is water is more readily oxidized than sulfate. And so for the cathode, they gave you the standard reduction potential of TL. So TL plus plus electron is TL, and that E value is minus 0.34 volts. And if you find the equation for water, water plus electron gives you half H2 and OH minus, and the E value here is minus 0.83 volts. And so, which one is more likely to be reduced? It's the value that is more positive. So in the cathode, TL will be produced because TL plus is more readily reduced than water. And so what I want to say about this part is that there are some teachers who say that H plus and OH minus are present in the solution. And so because of that, you can also think about this. H plus plus electron gives you 1/2 H2 and the electrode potential is 0. So you'd be like, hey, wouldn't H2 be formed instead of TL because H2 has a greater reduction potential value? But no, the new syllabus does not take into account H plus anymore. So the only case where you would take that into account is if your solution is acidic or basic. So you would have something like ammonium nitrate. Then in that case, that's an acidic solution. And that's when you would look at H plus as a reactant. So in general cases, you only take a look at water. So it's the last one now. So it's time zone 3. But time zone 3 is kind of long. So there are a lot of new things here. For example, this. So state and explain 2 properties of a liquid using the kinetic molecular theory model. So what's the first thing we could talk about liquids? So liquids are not stationary, they move, they flow. So liquids flow and they do not have a fixed shape. Solids do, yeah. Solids have a fixed shape, like this pen is gonna look like this forever, yes. Property 2, which not many people got correct, is that they're non-compressible or incompressible, meaning if you like push water molecules together, they won't change shape. And the reason is because the molecules are close together. So they're always very, very close together. So even if you push them even closer, they can't become closer because they're already in their maximum amount. Okay, then calculate the equilibrium constant. So you can see that they don't write equilibrium constant as Kc anymore. They just write it as K. When N2 is 30 moles, H2 is 40 moles, and NH3 is 6.17 moles at 55 decimeter cube. So I brought this question because IB usually gave you 1 decimeter cube volume. But now they give you different volumes, meaning you need to calculate the concentration yourself. And so if I calculate the concentrations for you, so N2 concentration is 30 divided by, so 30 moles divided by 55 dm cube, giving you an answer of 0.545 moles per dm cube. H2 concentration is 40 moles divided by 55 dm cube, giving you a value of 0.727 moles per dm cube. And in the case of ammonia, ammonia is 6.17 moles divided by 55 dm cubed, giving you an answer of 0.112 moles per dm cube. And so how would you find equilibrium constant? So K was equal to reactants on the denominator and products on the numerator. And if you substitute the values, 0.112 to the power of 2 divided by 0.545 times 0.727 to the power of 3, giving you a value of 0.0599 as your answer. So please read the question and see if they're concentrations or if they're moles. Okay, the second one was also kind of new because you're trying to draw what happens to N2 concentration when volume of the container is suddenly decreased. Okay, so what happens? So you decrease the volume, but you gotta remember that concentration is equal to moles over volume. So if volume decreases, the concentration of N2 initially increases. So it goes up. And then what happens? So since there's 4 moles and there are 2 moles of gas in the products, volume gets smaller, meaning that the equilibrium will shift to the side with less moles of gas. So it's going to shift towards the right. So EQ shifts right, meaning that the reactant, so your N2 concentration, will decrease again because the reaction is always going this way. And so when you draw how N2 changes, you would need to draw it as this. So first it needs to be parabolic, but they also accept linear. But you would make it parabolic because the rate of reaction is usually fastest in the beginning. And so also the equilibrium is established at this point, meaning that it should start becoming constant here. So an invalid answer would something that would look like this, because equilibrium is reached about here, right? And so this, you gotta be very careful as well. Oops, I think I raised too much. Let's take it back. Okay. Oh, sorry about that. Okay. So next question involves homolytic and heterolytic fission. But people don't really know how to define this. And so homolytic was if you have 2 electrons in a bond one electron goes to each atom. So each atom receives one electron. In a heterolytic fission, the two electrons go to one atom. So one atom receives both electrons is what we need to say. So remember the definitions, yeah? So number 6, a lithium-ion battery consists of lithium ions and lithium graphite and lithium cobalt oxide as an electrolyte. And so the lithium ions are produced at the anode from the lithium atoms embedded in graphite. And so state and half equation occurring at the anode. So it says lithium ions are produced from lithium. Oh, then lithium forms Li plus and electron. And it works because that's the anode, is where oxidation occurs. And number 2, comment on the sign and value of the standard reduction potential of lithium that makes it suitable to use in the battery. So this has an electropotential of minus 3.04 volts. So it says comment on the sign and the value. So the sign is negative and the value is very large. And why is that important though? Why would this be important for a lithium ion battery? Because what are we trying to do? We're trying to make electricity, right? And so this reaction, so reduction is not spontaneous. However, the oxidation process going backward is very, very hella spontaneous. And so since this reaction occurs very well, a large amount of energy is released that can be used by us to power up our electronic devices. And so you just need to say that the process of oxidation is spontaneous. Is all you need to say here. And the B, the lithium ion battery is rechargeable. So annotate the diagram below to show the direction of electron flow of electrons when the battery is recharging. So it's not discharging, but recharging. So if it's recharging, it goes back from the cathode to the anode. Okay? So if it were discharging, you'd go from anode to cathode. And if it's recharging, it's going backwards. And so our last page suggests why solar panels are often connected in parallel with lithium-ion batteries. Why? Because solar panels, they're going to absorb the sunlight, convert it to energy, which would be used to charge up our batteries. And why would you want to charge a battery? Because you want to store energy for the future. So all you need to write is store energy. And D, a charge of 1,000 coulombs passes through a lithium-ion battery during discharge. Determine the number of lithium ions released on the anode. So remember, Faraday's constant had a value of 96,500 coulombs, which is the charge carried by 1 mole of electrons. So 1 mole of electrons carry that much charge. And so, how would you calculate the amount of moles of electrons? 1,000 coulombs divided by 96,500 coulombs per mole gives you the moles of electrons, which is 0.0104 moles. But this is the moles of electrons, which would also equal the mole of Li plus. Because if you remember the equation, it's a 1-to-1 ratio. And so how would you convert moles into number? You multiply the moles by the one and only famous Avogadro's number, which will result in a value of 6.24 times 10 to the 21 Li plus ions formed. Okay, so the next question is about condensation polymerization. And the main example of a condensation polymer was nylon. And nylon was made from 2 functional groups, which was the amine group as well as the carboxylic acid group. And so it's asking for the two monomers that the polyamide nylon 6,6. So if you see which part's repeating, you can see like this part's repeating, that part's repeating, this part's repeating, and so on and so forth. And so if you write the first one down, it would have a NH2 group with CH2,6 and another NH2 group. On the other side, it needs to be a carboxylic acid. So COH, CH2,4, as well as another COH. So how do these monomers make the nylon? The OH and the H becomes condensed, forming water, and the NH-CO bond forms to form the bond called an amide linkage or amide bond, yeah? And so B1, the strength of nylon 6,6 is due to the hydrogen bonding between the polymer chains. So annotate the diagram to show a hydrogen bond between the sections of the polymer chains. So how is a hydrogen bond formed? Hydrogen bond is formed through a partially positive and a partially negative region of two different sections of a molecule. But it also requires that H binds to a NO or a F for a hydrogen bond to form. And so if you take a look at this, you can see there's an NH. And since N has a high electronegativity, N is partially negative, H is partially positive. And there's a CO double bond where O is highly electronegative, meaning that's negative, that's positive. And so you can label your hydrogen bond as follows. So there are hydrogen bonds here, here, and here. And the final question. So this question is very good for bio students. So it's a state the equation for photosynthesis. And so there's not many hints for what photosynthesis is. So you need to memorize this very, very carefully. So 6 CO2 and 6 water molecules will form glucose C6H12O6 as well as 6 O2 molecules. And so if you want state symbols, just in case, that would be, I'll just write it for you. Gas, that would be liquid, glucose is aqueous, and O2 is gas. And so last but not least, outline 2 advantages of using ethanol as a fuel instead of gasoline. So ethanol, where is ethanol made from? It's a biofuel, and usually it's made from corn. And you can use corn again and again and again and again, making it a renewable source. Oh, you can make corn again. You can't use the corn again, yeah? So you can make it again, so it's a renewable source. And also ethanol just inherently produces less CO2. And another good advantage is that there's less incomplete combustion. So you may know something called gasohol. So gasohol is when you mix gasoline 90% and ethanol 10%. And that reduces the amount of incomplete combustion, which is good for the car gasoline engines. Okay, so these are all the questions I've prepared for you that are new to this syllabus. And well, to be honest, 1B is also very new. So 1B, almost all questions in 1B, the content's not new, but the way you write the answer, the way you think is kind of different. So I will upload more videos on paper 1A, 1B, paper 2, on all the time zones in the near future. And because I think the questions in the new syllabus is a bit hard, I would like you guys to study more in depth, more in detail, and I will see you guys later. Thank you so much for watching.